Level 3 calculus, the 2025 exam is by the algebra of complex numbers and solving problems. This is the least examination in calculus. I think only about 20 to 25% of students do this one. But I'm going to be using a good old Casio calculator and the formula sheet which is given, was particularly these formula here, which directly pertain to real numbers. Okay, so with that said, let's do it to it. This question up is a classic remainder theory question, and specifically tell us that the remainder is 21 because what is divided by. So we have this divided by this, we get some number, and the remainder is this. What the remainder says is this. If we divide something by x minus a, we'll get the same remainder as if we put in a into the original equation. So it's minus 2 here, so then put 2 into this equation, and we'll get 21 back. So 2 to the power 4 plus p, we don't know what p is, but the x is 2 minus 4 times 2 plus 5, and that equals 21. 2 to the power of 4 is 16. 3 times 16 is 48. P cubed is 8. So 8p minus 8 plus 5 equals 21. So let's bring all of the numbers on one side and see what we get. So 21 minus 48 plus 8 minus 5 is minus 24. So 8p equals minus 24. Then p must be 2, 3. Fairly standard opening solver. The next one is really just a quadratic equation. We are asked to take this equation here and solve it for x, giving the answers in terms of k. All right, let's make the quadratic equation. We can write this as x squared minus 6k of x, k squared equals 0, and I guess we presume that k is a real number. K is a number anyway. Okay, so now let's use the quadratic equation. A is going to be 1, B is going to be equal to minus 6k, and C is going to be equal to minus squared. So x is going to be equal to minus b plus minus square root b squared minus 4ac all over 2a. I like doing the b squared minus 2a first. You've got to do it twice. So b squared is minus 6k squared minus 4 times 1 times minus k squared. So that's going to be 36k squared plus minus 4k squared, which is going to be 40k squared. Yes, makes sense. Okay, so let's a bit more like this. So minus b is going to be 6k plus minus square root of 40k squared all over 2 times 1, which is 2. Now, square root of 40k squared, can we rewrite this? 40 is 4 times 10, so that's going to be equal to square root of 4 square root of 10 square root of k squared to square root 10k. Yeah, do they make sense? Yes, that makes sense. It's just collectible by before the radical 2, so it'll make sense. 2k times square root 10. So now we're almost done. So x is going to be equal to 3k plus minus 6 divided by 2 is 3k plus minus k the square root of 10, which I guess you could maybe factorize that if you really wanted to. I don't wish it makes much of a difference, but that would be the answer. Right, well, this way, you're asked to prove the equation kx all squared equals 3 minus x over k has real roots for all values of k where k does not equal 0. So when they want roots like this, we have something squared. We're going to know at some stage we're going to need to do a. First thing I'm going to do is I'm going to expand out this brackets. This is when here, k squared, x squared. So k squared, x squared plus x over k. I'm going to bring everything over to the left-hand side. Minus 3 equals 0. Now we can find roots. Now this might not look like a quadratic, but let's make it a quadratic. Let's multiply both sides by k. See why in a second. And I get k cubed x squared. Remember, k is a real number. Plus x is x over k times k. There's just x. Minus 3k, which is a number. And 0 minus k is 0. Now we have a good old quadratic. Where a is equal to k cubed. B is going to be equal to 1. There's a 1 there. And C is going to be equal to minus 3k. And now what we want to do, we don't need the whole of the quadratic equation, but we need to know that the determinant is greater than 0. So that's b squared minus 4ac, that bit must be greater than or equal to 0. So in other words, 1 squared minus 4 times k cubed times minus 3k must be greater than or equal to 0. What's up with that? So 1 plus 12k to the power 4. 4 is greater than 0. Now we have the little bit of proof. So if k is is any number really, power of 4, it's going to be k is real number. K to the 4 is also going to be a real number. And 12 is a real number greater than 0. And k is not equal to 0. K to the power of 4 is a real number greater than 0. So a real number greater than 0 times a real number greater than 0 plus a real number greater than 0 must be greater than 0. Because 1 is greater than 0 and is a real number. 12 is greater than 0 and is a subset of real numbers. And k can be any number not equaling 0. So therefore k to the power of 4 must also be greater than 0 and be a real number. That's a little proof. Kind of proof. This one, I think, is really going to test our knowledge of Moivre's theorem and what complex roots are. So in z cubed means it's 3 roots, plus this equals 0. Even it's a real positive constant, that's good. Write your solutions in polar form. So like CIS. And then it's just applied Marcus theorem. So I want to rewrite this because this is messy. So z cubed is going to be equal to negative 8 m 27 I. I'm going to rewrite this as 8 m to the 27 negative I. It's just going to save me a lot of hassle later down the track. Okay, we can work out quite a few things from this straight away. We can work out the magnitudes are of this, and it's going to be equal to the absolute value of 8, which would be the same as 0, and which is 8 m 27. There's no way, plus or minus, it's going to give us the same number. Okay. The principal argument that is final theta that goes with negative I is something else. And it's a real pain in the neck to do it on these Casio calculators. It's just, yeah. And because I'll try to do it here, I'll try to do it in third form. I just will not do it. I know that the handheld calculators do it, but this emulator that Casio do, you just seem to want to play a game. The argument of negative I is minus 1.57 there. You should recognize that as minus pi over 2. Kind of makes sense because then we have negative I, we have the real and the imaginary axes. Negative I would be there. So this would be kind of there, and this angle here would be pi over 2. We're going the opposite way that we want to go, so it's going to be minus pi over 2. We could do 3 pi over 2 if we really wanted to, but I'm just going to leave it like that. And now we have enough to really apply de Moivre's theorem. Right. So de Moivre's, we have z to the power of 3. It's going to be equal to r, tells us that that is z cubed. It's going to be r to the 1/3 cosine principal theta I sine of that principal minus pi over 2. But I don't really like the way that they do that. I'm going to with I'm showing you a better way of doing it. So r to the 1/3, we know that is 8 m to the 27th. We take the cube root of that, and the cube root of 8 is equals 2, and that's going to be 2n9. So that's good to have. The z's, the zn is going to be r to the 3rd, which we've got. Then CIS, and the one that they don't give you is the principal argument, which is going to be pi over 2 plus 2k pi over 3 over n. Okay? Now, what are pi and the 3 bit comes from? Well, the 3 comes from the n. Pi is the principal argument, so it's going to be pi over 2 in this case. And k is going to be the numbers, the integer numbers up to but not including n. So it's going to be k is going to equal to 0, 1, and 2. There's 3 ways. So it's just an iterative process now. So Z1 and it's going to be equal to, when I say before, 2, 8, 2 n to the power of 9, which will be down here. Cosine, sine, pi over 2 plus 2 times 0, pi, which is 0, divided by 3, which is going to be equal to 2m9 CIS pi over 6. So negative. Okay. That's Z1. Z2 is going to be equal to 1. Always not X or A. So the R in third is always the same. The CIS is always the same. Now we have pi over 2 plus 2 times 1 is 2 pi over 3. So 2 pi minus pi over 2, and it's going to give us 2, so it's going to be 3 pi over 2, then we divide that by 2, 3 pi 6, which is going to be 2 pi, it's going to be pi over 3, so 3 pi over 2. It's 1, 2, 2. Well, eventually we got there. 2m9 CIS pi over 2. That's our second one. Now the third one, I think it's going to be really, really gruesome. So now we have negative pi over 2 plus 2 times 2, so 4 pi all over 3. So it's going to be 3.5 pi over 3. It's going to go, then it's going to go 6, 7 pi over 6. Yeah. Just going to pause. Yes, it does. So the way I worked it out is, so we've got 7 pi over 2 divided by 3. That's the same thing as 7 pi over 2 times 1/3, which is 7 pi over 6. Yes. It works. So here are our three answers as well. I like them. There's Z1, Z2, and lastly Z3. Tricky question, but you should be prepared for it. This next one looks like a zoo, and I think it is as well. Okay, so we're given a locus of points as described. So we have this point here and this point here. We subtract them, we find 4. So it's loci points, we have to convert it into this form here where A, B, and K are constant. Well, let's have a look at a couple of things. So for Z minus 5i, that in Cartesian terms, we would call that reference 0, 5. Okay. For this second one, we said plus 5i. The directrix of that would be the other way around, so it would be obviously 1 equals to 2. That's going to be 0 minus 5. D1 minus D2, that's going to equal 4. So that's going to, there's a quick fire way of doing it using Pythagoras' theorem, but I'm going to use complex algebra to solve it, just to go through the machinations of it. Okay, let's do this first one first. So Z minus Fi, the magnitude of that, that's going to be equal to the square root, using Pythagoras' theorem, of x squared plus y minus 5 squared. The other one, Z plus 5i, that's going to be equal to x squared. It's going to be the other way around, isn't it? Y plus 5. So far, so good. So we know we converted it to Cartesian. So we know that x squared plus y minus 5 squared minus this thing in here squared equals 4. And I don't like this BC here being having a negative sign. So square root plus y minus 5 squared is going to be equal to 4 plus x squared y plus 5 squared. So plus. Okay, right now. Well, we get the square both sides. The left-hand side is going to be pretty easy because when we square this, the radical sign is just going to disappear. Y minus 5 squared. Now, remember when we square two things, a plus b squared, we get a squared plus 2ab plus b squared. So a squared, a is going to be 4, so that's going to be 16 plus 2 times 4, which is 8. This thing plus x squared plus 5 squared. So I might be asking why did we do that? Well, we did that because we can simplify things a lot now and then deal with this thing a bit later by squaring in the end. So let's see. Let's break out all of the brackets that we've got. So x squared plus now y minus 5, y minus 5. So this is the left-hand side. So we're going to have x squared plus y squared minus 5y minus 5. Y is the same setup as this one here, plus 25. So that's going to be x squared plus y squared minus 10y plus 25. Okay, so we're just going to leave this here and we're just going to park this. This is the left-hand side. Let's deal with the right-hand side. So 16, going to not worry so much about that nasty bit in brackets. I'm just going to do it at the end. Plus x squared plus y plus 5 squared. And that's going to be equal to 16 plus x squared plus y squared plus 10y plus 25. Plus, of course, this nasty thing here, the 8 square root squared plus 5 plus y plus 5 squared. Okay, so why did we do all this? Well, this is the left-hand side, this is the right-hand side. We can now set them up against each other and simplify as much as we can. So it's all in one big nasty file. So x squared plus y squared minus 10y plus 25. That's these ones up here. Must be equal to 16 plus x squared plus y squared plus 10y plus 25 plus this nasty thing here. Okay, can we cancel? Yes, we can. We can cancel the x squareds, cancel the y squareds. We can't get rid of the 10y, but we can take 10y from both sides, so we have negative 20y now. And we can take 16y from both sides, so that's done. And we can get rid of these 25s. 25s will cancel. And now we have something which is a lot easier to deal with. Right. Now what do we do? I can see a little bit of simplification. We can divide everything by 4. So minus 5y minus 4 equals 2. I'm just basically here. Again, there is a way of doing this, but I just prefer this method because it always gets the answer. We get to see the mechanics of how it comes together. Now what are we doing? We want to get rid of this nasty beastie thing here. We could divide both sides by 2. We could do that, but I'm not going to. This stage, I'm going to square both sides. Okay? I'm going to, at the end of that, get this. That's going to square. And then we're going to get this thing. Brackets here. Fantastic. We're nearly there. Nearly there. All right. Let's have a look at this left-hand side. So minus 5y minus 4 minus 5y minus 4. That's going to give us 25y minus 20y minus 20y plus 16. So that's the left-hand side. And let's do the right-hand side. So we need y plus 5 squared. Did that. It's going to be y squared plus 10y plus 25. Okay. And now we're approaching something that we can actually just solve it and just simplify. 16 is going to be equal to 4x squared plus y squared plus 40y plus 100. All right, so it looks like a mess, but we're getting there. We just have to sort of chug along. Okay, what do we do? This is going to be, it should have been yes, 5 minus 5y times minus 5y. 25y. Okay, we're almost there. Let's collect up everything and wrap the show up. And this should be plus 4, shouldn't it? Yes, that makes things a lot easier for us. Right, so with all of that, let's go to the end. So what that means is that these 40 y's will cancel. Let's take 16 away from both sides to get into 1. So 25y squared minus the 4y squared minus the 4x squared. That's gone back. It's there. Equals 84. We're nearly there. So 21y squared minus 4x squared equals 84, which is the hyperbola that we were looking for. Oh, thank goodness for that. Yeah, be really, really careful with your pluses and your minuses there. I had a few false starts where I had to pause the video and I thought that doesn't make any sense. Be really, really careful. This just there is a quick right way of doing that. Maybe I'll do it later on. On to question 2. And hear a little noise there. It's a little fan that I've got. It's a really, really hot humid day. So this is you here. So you is 4 in the real plane. Your axis plus 2 on the imaginary axis, and W -2 on the real plane, and -3i. So we want to find Z equals 2u plus 3w. So 2 plus 2i is going to be equal to 8 plus 4i, and 3w is going to be -6 minus 9i, and they want us to get these together. So 8 plus 4i minus 6 minus 9i. It's like I just did them all on one line. So it's going to be 2 minus 5i. So Z, it's going to be 2 minus 5. So 2 across and 5 down. So Z is going to be here. I mean, you could draw the lines there, but if I've got the dots here, that's fine. On to B. So U is NCEA 3 pi over 10. Write U to the power of 5 in the form A plus BI, and both real numbers. So for this one, we are going to use Moivre's theorem, the one that's given to us in the notes. It's going to be this one, series of n times the principal argument. And I guess we could say that the principal argument is m is going to be r. Okay, so use 5 therefore. That is going to be equal to m to the power of 5, CIS 5 times 15 pi over 10, which I think we can simplify, can't we? Surely IS, what's it going to be? 3 over 2. 3 pi over 2. All right, but there's none necessarily in the form that we want. So CAS L theta is, of course, cos theta plus sine of theta. So it's going to be m to the power of 5 cosine of 3 pi over 2 plus sine 3 pi over 2 I, as brackets. So cosine of 3 pi over 2, I think it's 0. 3 pi by 2 is 0. It's good. So m to the power of 5, 0, and I think sine of 3 over 2, I think it's -1. For memory, sine 3 pi over 2, -1. Hey, good memory. -1. So we can rearrange or something, bring this negative sign out front. So use the power of 5 as negative by m times I. Yeah. How about that? Ranging right along. Again, if you can hear that little buzzing noise, it's a little fan that I've got on the desk. I live in Wellington, so hot days, you've got to make the most of them, as we don't get many. So we're told that the modulus of 5 minus mi equals square root of 5m squared, where m is a real number and we want to solve for m. So in other words, the end of us we want to equal something. Okay. If you remember right back to when we did complex numbers, that's going to be the same as using Pythagoras' theorem, a squared plus b squared, where a is going to be 5 and b is going to be negative. So modulus 5 minus m is going to be square root of 5 squared plus negative m squared, which is square root of 25 plus m squared. Okay, so given that, let's set this equal to length. So square root 25 plus m squared is equal to 5m squared. Right, let's get rid of, let's square both sides. It's going to be pretty easy, pretty trivial in this case. 25 plus m squared equals 5m squared. So yeah, let's take an m squared across. So 25 equals 4m squared. Up here, m squared is going to be equal to 25 over 4. So therefore m is going to be square root 25 over 4 plus minus. So that's going to be plus minus 5 over 2, which then I would say 5 over 2. That's our answer. So now we have this big beastie here. We need to find all the values of g and h and set equal to each other. So let's just expand out the brackets and see where we go. Let's do the right-hand side first. So 10 minus 4, 3 minus I, it's going to be equal to 3 times 10 is 30 minus 12i minus 10 minus 4i. Now remember, minus 4 times minus, plus 4. Now remember, I squared is negative 1 by definition. So we can rewrite this as 30 minus 22 minus 4, which is 26 minus 22. So far, so good. Now let's deal with the right-hand side. So the right-hand side, sorry, the left-hand side. So g plus 2i, 3 plus hi. Okay, so we have 3g plus 6i plus ghi, g times hi, plus 2hi squared. Squared by definition is minus 1. So we can rewrite this as 3g plus 6i plus 3hi minus 2h. Now we can separate out the imaginary real parts. So that's going to be equal to 3g minus 2h. So this is the real part plus 6 plus gh. Alrighty, and this is the imaginary coefficient. Okay. Now I think we're just going to set these off against each other. So we have 3g minus 2h plus 6 plus gh I equals here 22 minus 26 minus 22. Now I think we set the real parts equal to each other and the imaginary coefficients equal to each other. It must be true. Equals 26. Yeah, they must be true. And the imaginary side, 6 plus GH must be equal to minus 22. And now it's an algebra problem. What we'll do now is we'll solve this one for H and then sub it into this one. So G times H is going to be equal to minus 28, because 22 minus 6 is that. So H is going to be equal to minus 28 over G. If we have an H in this one, you can put G. So 3G minus 2 times negative 28 G equals 26, and we have one equation and one unknown. So you've got 3G minus 56 over G equals 26. How do we solve this one? Well, I'm going to multiply everything out here by G. I'm going to turn it into a quadratic equation. So 3G squared minus 56 equals 26G. It's a nifty little trick. It brings 26G over, and now we have a quadratic in G. So now we can solve for G. So G must be equal to two distinct numbers. So we go to Mr. Casio, and I'm just going to be completely lazy. We've done all the legwork, so I think we can get away with our polynomial solving. It's degree 2, 3, minus 26, minus 46. We get those two numbers there. No, we don't. I just think this is going to be plus, isn't it? Because negative 2 times negative is going to be plus 56. It's a hot day. I thought those numbers sound weird. Okay, so it's going to be plus 56. 56, not negative 56, and our answers make a bit more sense now. So we couldn't really have G and H that bigger than, much bigger than 3. So 14 over 3 and 4. Okay, so now we've got the two answers for G, and we can use this one here. So G times H equals negative 28. So let G be equal to 4. H equals negative 28. H is going to be equal to 28 over 4, which is going to be a nice whole number. Is going to be a nice negative 28 divided by 4. Oh, it is a nice number. All right, 7. H equals negative 7. Now we're going to leave 14 over 3. H equals negative 28. So H equals negative 28 times 3 over 14. 28 times 3 is 84 over 14. Negative 84 over 14. Don't think that's going to simplify. Yes, it does. Negative 6. So H equals negative 6, or I'm blithering away. So the answers that we have, G can be equal to a set of 14 over 3 and 4, and H can be equal to negative 6 and negative 7. That's that. Oh, thank goodness. This next question I really like. It requires you to know quite a bit about the mechanics of complex planes, again, diagrams, what arguments are. It's really nice question. Let's see why. See the pi over 4. Now, pi over 4, let's do a little graph. So this is the real axis, it's the imaginary axis. Pi over 4 is here. Sort of layman's terms, it's 45 degrees. It's really, really great because 4 is 1. And we know that tan of the argument later is the imaginary coefficient over the real coefficient. And if that equals 1, the only way that can be true is if the imaginary coefficient equals the real coefficient. The imaginary part and the real part. That's going to be really, really good for us. Okay. So that said, let's kind of deal with this BC thing here and set it to, we'll find the real part, the imaginary part. We don't need to deal with pi over 3 anymore, I think. And the real part will equal the imaginary part, and we'll be able to solve for D. Sound like a plan? All right. So how do we do it? Well, we do it by conjugate. 6i over 1 minus d I have to be careful by 6 these. We're going to multiply this by 1, but it's not going to be, well, it's just by 1, it's going to be conjugate of the denominator. So that over that, it's the same, that equals 1. It's the same as multiplying by 1. Okay. So at the top, we've got d plus 6i times 1 plus di. Let's do the top and the bottom separately. So the top is going to be d plus 6i. Just get my way now. Let's do the boundary here. Plus 6i. It's going to be d times di is d squared plus 6d times 6 I squared. And we know by definition that I squared equals the numerator is therefore going to be d plus 6i plus d squared I minus, again, I want to put the 6 first, 6d. Let's simplify that in. But let's separate it out into its real and its imaginary parts. So the real part, we have 6d can. So minus 5d is our real part, plus 6 plus d squared, it's our imaginary coefficient for the top. Yes, so now the imaginary part is going to be the same mechanics. So 1 times 1 is 1 minus di plus di. So the thing about that is that they disappear. And minus, so minus d squared ice, isn't it? So that's going to be equal to plus d squared. So 1 plus d squared, which you see are all normal, which are all real. Let's collect what we've got so far. So we've got this thing at the top, minus 5d plus 6 plus d squared over this thing. Okay, now I'm going to separate that because these have the same denominator. The minus 5d over 1 plus d squared must be equal to I times 6 plus d squared over 1 plus d squared. And remember, so this is the real part, real coefficient, and this is the imaginary coefficient. So they must be equal, so we can eliminate that and set equal to each other. So sad. I think I might have jumped a step here. It'll make sense. So minus 5d over 1 plus d squared equals 6 plus d squared over 1 plus d squared. And if they're equal, then at the top there must be the same. That the ones at the bottom must equal x, and multiply it by this, you can cancel. So we're left with minus 5d. It's going to be equal to 6 plus, I think I'll do that. So now it's really quadratic, isn't it? So let's bring this d over and make it equal to 0. So d squared plus 5 plus 6 equals 0. I brought this back and swap sides. So now it's a quadratic. And we want to factorize that. It's going to be 3 and 2 is like d plus 3 and d plus 2 equals 0. So d can be minus 2 minus 3. So for this one here, I kind of expanded this out. So maybe I'll do it like that. So minus 5d plus 6 plus d squared, all I want 1 plus d squared. And it's the same thing, minus 5d over 1 plus d squared plus 6 plus d squared 1 plus d squared. All right. Well, we know from, because n or pi over 2 was 1, that the real part must equal the imaginary. So what I did then is I set minus 5d over 1 plus d squared equal to 6 plus d squared over 1 plus d squared. Now I'm going to multiply both sides by 1 plus d squared, which is going to eliminate that. And then I'm going to have at the top here 1 plus d squared. And they're going to cancel 1. So we're going to be left with 5d equals 6 plus d squared. Brought this 5d over. So I had 6 plus d squared plus 5d equals 0, and solve like a regular quadratic. Maybe that's a better explanation later. Either way, it's a really, really good question. Question 3. The end is in sight. So we have a quadratic equation with real coefficients. One of the solutions is this, where this is a complex number. What do we know about it? We know it's quadratic, so there are 2 roots, 2 solutions. And we know that this is one of them. Well, if one of the solutions is a complex number, the other solution must be its conjugate. So 2 minus square root p I must also be a solution. What else do we know about quadratics? Well, we know that x squared minus the sum of the roots, x, plus the product of the roots equals 0. Back to cast your eyes back many years ago when you first came across quadratics. So therefore, if we know the product and the sum of these roots, we can want this to our heart. Okay, the sum of the roots, 2 plus, seems like same type, square root p I plus 2 minus b square root p I. So there, so you can cancel, and we can be left with 4. So x squared minus 4x plus something equals 0. So we're almost home. Now we need to know the product of these two. Well, let's do it right now. So 2 plus square root pi, 2 minus square root p of I. So I'm going to set up my right here. 2 square root of. So it's going to be 4 plus 2 square root p of I minus 2 square root p of I. It's good. They're going to cancel out. And lastly, we have square root p I times minus square root p of I. And that's going to be minus p I squared. Yes. And we know that I squared by definition is minus 1. So this equals e. So the sum of the roots is 4 plus e. I always have trouble with not ones, these out as well. I have to do them in sort of group form. So our equations are complete. And I think that's all you can do. So our final answer is going to be there. There you go. Right. Expand and simplify. Give me your answer. And when we multiply, remember when we multiply any bracket out, we always get this sort of pattern here. Okay. So A is going to be A. It's going to make it since there's nothing in here. Okay. Square root is 3a times the square root is 3a. Let's do the b squared. So b square root of 12a I square that. So that's going to be 12a I squared. And I squared is negative 1. So that's going to be to negative 12. So that's that bit done. Now we need to do the negative 2 times square root of 3a times the square root of 12 I is inside the radical. How are we going to do that? Well, it's going to be 2 times, so minus 2 times that. It's going to be minus 2 times combine what's radicals. I stays there. So negative 2 times square root of 36. That's good because that's x squared, I is equal to minus 2 times 6a, I equals negative 12a, I. Okay, collecting all of this together, we can expand it now to 3a minus 12ai minus 12a. I think that's correct. That is correct. So now you need to simplify things out. This is going to be minus 9. So it's going to be minus 9a minus 12ai. Maybe we can vectorize this a little bit. Minus 3a, 3 minus 4i. Maybe we can do that. Either way, we get the same answer. Right, next one. We need to expand out some brackets, solve for x. So x equals some number. So this lineage at the left-hand side is a bit nasty, so let's simplify it a little bit. 3 plus 2 squared. So when we simplify it, what are we going to get? 3 plus 6 squared x. Let's finish this. Let's do this. Plus 2 squared x. And 2 squared x, 2 squared x. It's going to be 4x. Square root times square root is x, 2 times 2 is 4x. So we can simplify that a little bit. Plus 8 square root x plus 4x. So it's the left-hand side simplify. Now, can we do anything else to it? No. So now let's set the left-hand side equal to the right-hand side again. And I think we're going to need to solve. I think we're going to need to turn this into a quadratic. So let's take 5 away and take 6 square root x away, set that equals to 0. Now this might not look like a quadratic. I'm going to do a little fancy switcheroo here. So let's simplify it a little bit first. So 3 minus 2 minus 5 is minus 2. 8 square root x minus 6 square root x is 2 square root x plus 4x there equals 0. That's been taken care of. Can we simplify this a little bit? Well, let's divide between 2. That's going to make our life a little bit easier. So negative 1 plus the square root of x plus 2x equals 0. Makes our life a little bit easier. Although we've got this square root here. So I'm going to do a little switcheroo. I'm going to say let v be equal to square root of x. So now we've got 2v squared, because it's going to be 2x, plus v minus 1 equals 0. And we're not going to solve those, hopefully. This could be a nice one, but minus 2. Yeah, we can actually do this just by factorizing. These scared me in a second. So 2 times negative 1 is negative 2. So we want 2 numbers that multiply to give us negative 2 and add to give us positive 1. It's going to be positive 2 and negative 1. So I'm going to rewrite this again. 2b squared plus 2b minus 1b minus 1 equals 0. Let's factorize the first bit. So 2b is common, b plus 1 then minus 1 is what they have in common. V plus 1, same. 2v minus 1, v plus 1 equals 0. It's up a little bit. So 2v minus 1 equals 0. So v must be half in that case. V plus 1 equals 0. V equals -1. But remember, we didn't start with v. We started with x, and v is the square root of x. So for this one here, the square root of x equals a half. X is going to be equal to a quarter. And for this one, square root of x equals -1. This is no solution. There's no solution in this. So our only solution, viable solution, can be x equals a quarter. It's our one answer, I think. I don't think there's any other way that we can solve that one. Not today. We're almost there. One question after this one thing. And I think for this one, we're really going to have to use Focus algebra to solve it. Right, so just looking at this guy, there are 3 solutions. So one of them is given to us, which is convex imaginary form. So the other one's real form. It might come in groups. It tends to be a real solution. Okay. First solution is going to be really easy. If z equals 1 plus I as the solution, then its conjugate, z equals 1 minus I, must also be a solution. Okay. Now, we also know from the previous example that quadratic in z squared plus the minus the sum of roots, sum of the solutions, x, y, z in this case, z in this case, plus the product of 2 solutions must also be the factor. Okay, so let's work out the sum. So the sum is going to be 1 plus I plus 1 minus I, which is 2. Product, so minus 2 is going to be, so minus 2. Z must be a negative minus. So 1 plus I, 1 minus I, when we multiply them out, we get 1 plus I minus I minus I squared. I squared is minus 1. So this is 1 cancel plus 1, which is 2. So that tells us that z squared minus 2z plus 2 is a factor. So when we multiply this by something else, we must also get what we started with at the top. Okay, so let's see how far we can get. So we know that z squared minus 2z plus 2, we're going to be timesing by something z plus constant. So let's call this alpha z plus beta. It's going to be equal to the original equation, which is 3z, what was it, 3z cubed plus bz squared plus qz times 8. Okay, So what do we know about alpha and beta? We know that leading to here is 3z cubed. Only way we can get z cubed is z squared times alpha and z. So therefore, alpha must be equal to 3. We also know to get this negative 8 here, this 2 times beta must equal negative 8. So 2 beta equals negative 8. Beta must be negative 4. So here we go. We're almost there. Don't know whether this is actually required, but it tells us that 3z minus 4 is a solution. So therefore, z must be 4 over 3 must be one of the solutions, which is indeed a real solution, which is what we expected when we first started. But that doesn't really help us. So we need, because we're trying to find what P and Q are. So the way we're going to do that is we're going to expand this out. We know what A and B are. What alpha and beta are. 2z plus 2. And that's going to be, what did I say? 3z minus 4. We can expand out that bracket and see what we get. So a bit. So z times 3z, z squared times 3z, that's 3z squared. Minus 2z times 3z is minus 6z squared. 2 times 3z is plus 6z. Now it's 4 minus 4z squared plus 8z minus 8. Collect them up and we get 3z squared minus 10, cubed squared plus 14z minus 8. And that's almost what we started with. P and the Q are now known. So the P must be negative 10 and the Q must be positive 14. I think we're done with that one. I think that's all we wanted. Good question. Up until now, I've been avoiding using calculators. You can see the algebra player. I'm going to use the calculator in this thing because it's going to be very horrible. So we're told that U would be a complex number. So in other words, U is going to be A plus BI, and B is going to be C plus DI. That's what we're going to get as our answer. I don't particularly like this one. It's got to be the same form before we can really use simultaneous equations. So what am I going to do? I want to kind of massage this bottom one here so that it looks a little bit like, get rid of this extra bracket here. So U plus B minus B I equals 4. That's going to be it. So there's an I in there, top one. So I'm going to multiply everything by I. So we can do anything as long as we do it to both sides. So U I plus B I minus B I squared equals 4i. I squared is negative 1, so this is UI plus B plus B equals 4i. I'm going to call this equation A, this B, this one is C. So from that, I'm going to subtract the first one, I think. because it has this ui business. Minus ui plus 2v equals 3. I'm going to subtract all of this. I'm going to get vi minus v equals 4i minus 3. So let's figure out v I minus 1. Now we almost have it. So here, so v is going to be equal to 4i minus 3 divided by I minus 1. And for this, I'm going to use the calculator rather than doing conjugates. So option complex numbers 4i minus 3 divided by I minus 1. So 3.5 minus, so 3.5 minus half I. I'll be putting the I first. So I'm going to say minus half I plus I, and that causes 7 over 2. 3.5. So V is done. Now let's look at U. Now that we know what V is, we can just substitute it into this equation up here. So U I plus 2 minus a half I, that's going to be nice, plus 7 over that's going to be nice as well, equals 3. And now we can solve for U. So U I plus half times negative half I is going to be minus I plus 7 equals 3. So, right, nearly there. U I, let's bring this I over. It's going to be equal to I minus 4. So now we have this I. So only 1 over I is equivalent to negative I. Don't leave me. So 1 divided by I equals negative I. So if we have, so U is going to be equal to I minus 4 divided by I, it's going to be 4, positive 4i plus I squared, which is negative. Let's use the calculator. I'm too tired. So I minus 4 divided by I, it's going to give us 1 plus 4 plus 1. So use that, and B is minus half I plus 7 over 2. And that is the end of that. Thank goodness. That's our answer. That's the end of exams. I'm not a big fan of complex numbers. You can see absolutely 20 to 25% of students do them. You do use them really specialty things, electrical engineering, stuff like that later on. But yeah, I can understand why you take it. It's good practice for your algebra though. So I hope you enjoyed that.